Okay. So far we covered modeling and simulation, what is the difference, and we covered modeling for simulation. I mean analytical modeling in order to create simulation models. Today we'll cover another way how can you use modeling for control. So do you remember what means simulation? Act of using. Modeling is act of building. Why do we need modeling for simulation and for the control? And right now we will talk about the control aspect. So I hope that you remember this, that we covered already. All right, let us talk about the control. What do you understand by control? It's like we have an object that we want to control. What do we mean by that? That we want them to produce motion or forces or torques or other kind of behavior in a way that we want, and we need to act on this object such as the result behavior was the one that we want. When we talk about robotics, we need to consider that there is always a robot, right? It's a bunch of mechanisms, of links, joints that attach together, and we can measure the motion and forces using sensors. And if we'll just leave it like this, it will be just a pendulum, for example, a passive system. But and the motion will be just chaotic, random, uncontrolled. But we want this motion to follow some predetermined trajectory, maybe, or predetermined behavior. And this is why we need to act on these dynamics. We need to apply forces and torques, such as the motion will be, the motion will make sense. We use actuators and transmissions in order to do this. In order to control the transmissions, we use amplifiers with the local feedback system. And in order to make some conversation between all these aspects, we use controller. And as the input, we use desired behavior and current state. We measure the difference between the current state and the state that we want. We calculate the error, and the controller has to act in a way such as to decrease the error. Okay? So it's in general, but in the scope of our course, we will skip this part, and we will think like a controller produce forces and torques directly to the dynamics of our system. So real robots are subject to the flexibility, noises, vibration, friction, backlashes, saturation, limited resolution of the sensors, and all other problems that we can have in real life. And all of this is beyond of our course. We're not going to tackle them. Okay, I mean, you can do it by your own, in your own projects, if you want to. All right, so when we talk about robot, for example, a robot manipulator, robot can act as a source of motion, a source of forces and torques, or to act as a spring damper or mass, just like this. I mean, this equation is essential for our course. It will be everywhere. And right here, we mean that if we want to create a robot that interacts with the environment, it also has to be compliant. And in order to do this, we use hybrid force motion controllers. And we will cover all of them within this lecture. Okay. Let us talk a little bit about model-free control. What it means? That actually, in order to tune a PID, do you familiar with PID controller? Can you raise a hand if you're familiar with PID? Really? You don't know about PID control? Okay. So it means that you need to read the chapter 8 in the book of Kevin Lynch. And right now I will give you just a small portion of this material, but PID control is just essential for the whole course of robotics. And without understanding the PID control, it's just, you cannot go anywhere. Okay, so what is the idea? It's like, let's assume that we want to do a position control. Position control, it means that robot is isolated and it do not operate with environment. It means that we can use this robot, for example, for welding. If we do welding or we want to paint something, we have just a spatial trajectory and we need to follow this trajectory. The robot has not to generate any forces or torque. So the force of interaction will be 0. This means position control. And if we just follow the trajectory, we need to apply torques such as it follows the trajectory, right? It means that we can compute the difference between the desired trajectory and an actual one. And controller has to make this error as small as possible. If the error equal to 0, the robot will follow the predefined trajectory, right? Let's us make a physical example. Let's assume that my arm is a robot link, and in the very first moment of time, initial position equal to 0. Let's assume that we send a signal, go to the position of 1 radian, like this. And in very initial moment of time, we have an error. An error which equal to desired minus actual. Desired equal to the 1 radian, actual equal to 1 radian. So the error is equal to 1. So we need to produce enough force in order to go there. It is our task. So physical analogy will be the following. Let's assume that this 1 radian is the position of rest. Since we want to go to this position, we nominated this position as the state rest position, right? And it means that in very moment of time when we just send the signal, we change the position of equilibrium. It's like we already have a spring that's been stretched, and we can think about our controller as another spring and damper system that's been stretched. So it's like 1 radian now is the position of equilibrium, but we stretched it and it bounced like this. So we can think about our controller as a multiplication of coefficient of stiffness times the error plus coefficient of damping times the derivative of this. It's like a mass and a damper. We can draw a picture. Suppose that it is equilibrium position. And at this angle equal to the desired angle. And right here we have a spring and a damper. Okay? And a bad controller will behave like this. A good controller will behave like this, without overshooting and without steady state error, and it will do this very fast. And actually, this one is called PD control. PD, it's P stand for the proportional. This is a coefficient of, this is a proportional coefficient. Why it's called proportional? Because our torque is proportional to the error. It's a D because derivative. And it's a physical analogy of PD controller. How can we test how well our controller works is to specify a non-initial error, just as I wrote you here. So here you can see a plot, but here it's like in this picture we go from the position of 1 radian to the 0. It's like opposite. Okay. So we can test how well our controller works is to specify non-zero initial error, and we can see how quickly and how completely the controller reduces the initial error. It takes time to reduce error. The error may be never completely eliminated, and a typical error response can be described by, first one, transient response characterized by the overshoot. It's like we have very stiff spring and we have oscillation, and because of that we have overshooting. And also settling time, it means how fast the plot will go to the 2% region. And also a steady state response characterized by the error E steady state. It's like here we worried about overshooting, we worried about how fast our controller works, and we worry about steady state. And all these three components, actually, they stand for each component of PID control. It's like, so I already explained you this physical analogy. PID control looked like this. So P, Kp, and Kd we already considered. And beside that, we also have Ki. Ki is a coefficient which is multiplied with the integral of our error and it allows us to eliminate steady state error. It means that let's assume that we have this kind of response. If we increase coefficient of proportion coefficient, it will be like this. Maybe the overshooting will be bigger. So in order to increase speed, we need to increase coefficient of proportional coefficient. In order to get rid of damping, what kind of coefficient we need to increase? Derivative one. So if we increase not like this, eliminate damping, overshooting, we need to increase KD, and it's probably look like this. And in order to get rid of steady state error, we need to increase the I component, Ki, and then it will look like this. So right here at animation, you can see we're increasing P component, now D component, I component, and now D component in order to get rid of overshooting. So once again, we increase Kp proportional, then integral to eliminate steady state error, and then damping. So damping, it's like friction, right? If you have very huge friction, your system will not bounce. But also it means that you waste a lot of energy. That the torque, the final torque will be very high. Okay, is it clear now? For those who did know about PID control, I encourage you. Actually, it is for all of you. I encourage you to read the chapter Robot Control and the Modern Robotic book. It's very great. I mean, it's a good explanation from the beginning. Even if you think that you're very good in control, still you will find a lot of useful information. At least you will just repeat it. Okay.